Hello, I'm Patrick Kuiper, and I'm a PhD student at Duke University's Department of Electrical and Computer Engineering. I'm also an active duty major in the U.S. Army. I'm joined today by Suri Lin, a PhD student at Stanford University, and Christopher Canella, who is also a PhD student at Duke University in the Department of Electrical and Computer Engineering. We're here to discuss a proposal for investigation regarding data analysis to support the U.S. Army's prognostic and predictive maintenance effort, also known as PPMX. For this discussion, I will quickly provide background on the U.S. Army's PPMX initiative. Chris will provide a high-level technical details for his time series analysis research, which is well-suited for the PPMX dataset. And Suri will provide a framework for applying a data-driven optimization, operations research optimization to make practical recommendations based upon the PPMX dataset. To briefly introduce the PPMX dataset and initiative, this effort is a program providing tools via equipment sensors and data analysis, which give real-time information to commanders in the U.S. Army to make decisions regarding maintenance of equipment. These are often vehicles and weapon systems. We don't currently have the exact data set being generated by the PPMX effort, but instead are using a data set generated by a previous effort called the Conditions-Based Maintenance, or CBM Plus initiative. The fields associated with this data set, which can be seen on the screen under the data column, are very similar to the PPMX initiative, and the analysis we conduct will therefore be applicable to the data generated by PPMX. The goal of our analysis is to provide tools to accompany the data generated by the PPMX initiative. Here we can see some examples of a data visualization provided specifically by the CBM Plus initiative, but which is very similar to the PPMX program. We can see here that the data is given by vehicle sensors. For example, each column is different sensors, and each row is a different vehicle. So for the first column, this gives an example of engine coolant temperatures, the second column, fuel rates, engine oil pressure, and so on. And then accompanying this data set are outcomes. One attribute of this data set is that it is imperfect in many ways. There are many readings, and it is a time series analysis, so the readings are distributed over a specific period of time. And there are outcomes associated with the vehicle or piece of equipment in question. You can see that in the at the side of this visualization here. But one issue associated with it is balancing the data set so that outcomes are evenly associated with readings from each of the vehicle sensors. And this will allow us, balancing the data set will allow us to more accurately model the outcomes associated with of the vehicles or piece of equipment in question. To talk a little bit more about a potentially useful data analysis framework, I'll hand it over to Chris.
Hi, I'm Chris Canella. So whenever we are working with time series data, we're attempting to predict multiple unobserved values. One of the key challenges that we have in this modeling is how do we incorporate prior information about the variables that we've observed and the values that we've previously sampled into our model or into our architecture. So as an example, consider trying to predict 2 unobserved variables based on 3 other observations that we currently have. Next slide, please. So we want to sample from that joint distribution of the probability of x3 and x4 given x1, x2, and x5. We can auto-regressively model this by breaking it down and saying, okay, well, we'd like to sample x3 given what we've seen in x1, x2, and x5. And then we might go on to say, okay, well, now we want to predict x4 given what we sampled in x3, and then what we also saw in x1, x2, and x5. Next slide, please. And so all that conditioning information of x1, x2, and x5, and x3, x1, x2, and x5, that's all the prior information that we try to throw into our models. And that's really answering the question of, well, do the samples that we're creating make sense given what we've seen and what's been sampled? Next slide, please. And a recent architecture, a very recent architecture that's come out is called Tactus, and that really attempts to incorporate this prior information by using a transformer to encode and encapsulate all that prior information for our predictions using self-attention. Next slide, please. And as a high level sort of view of the Tactus architecture, what it's doing is it's using transformer-based self-attention to encode and really capture global information that's relevant to sampling all of those unobserved values that we're trying to predict. Next slide, please. And it's also using a decoder mechanism that takes what we've previously encoded and uses that to generate the distributional parameters for the missing values that we're attempting to sample. Next slide, please. So as a general sort of view of what this looks like as it's operating, we have a stream of some original data. Next slide, please. And the encoding side is taking a look at every single observation and every single value that we're sort of looking at. And it's using self-attention to attend to every other value. And it throws all of that into an encoded representation of every variable that we're looking at in the time series that's both observed and that we're trying to predict. Next slide, please. And after that attentional encoding layer, we take those encodings and then we, for every value that we're attempting to predict, we then attend to every single latent encoding that we've generated in order to produce a sampled value. And so Tactus is going through these attentional layers where it's essentially looking at everything that's sort of present and using all of that information to feed into either the encoding or into the sample that it's creating. Next slide, please. So there are some advantages and disadvantages to this Tactus model. The main advantage that it has is it's a very natural, it's tokenized representation of time series, and its use of an attention mechanism is really naturally suited to modeling time series. And it's also very naturally suited to handling missing values and asynchronously observed values. At the same time, this use of self-attention is computationally very expensive. And it's a significant problem when a large fraction of your data is missing. And this is quite problematic when you're trying to handle asynchronously observed time series. And the reason for that is for every variable that you have in an asynchronously observed time series, the number of variables that Tactus is attempting to represent within it grows quite a bit, and it becomes memory inefficient to model an asynchronously observed time series with this self-attention mechanism. Next slide, please. So part of our research is how do we improve on this novel mechanism and make it actually practical to employ in situations involving high dimensional time series that are asynchronously observed that have a lot of missing values. And one of our improvements is to introduce perceiver-based encoding into this architecture. So we replaced Tactus's transformer-based encoding with a perceiver-based encoder. And so rather than using an encoder that takes a look at, that attends to every single other piece of information that we currently have in order to generate an encoded representation of our variables, we attend to a set and learned a learned set of latent variables, and this significantly reduces the amount of memory that's required for the encoding step of Tactus. Next slide, please. So using a perceiver drastically reduces the memory requirements of employing attention mechanisms. And this enables processing raw streams of multimodal inputs. And it's enabled the joint processing of audio-visual time series. So transformers are typically more suited towards applications such as text processing, because the memory requirements of processing text are quite a bit lower than processing video streams. But with the perceiver architecture, the memory requirement is so reduced that you can start to apply attention mechanisms to analyze things like streams of raw pixel values in a video alongside the audio waveforms that are accompanying it, or streams of raw pixel values to predict properties of the optical flow within the video. And those are some of the introductory examples that were introduced by the original authors of the perceiver mechanism. Next slide, please. One of our other improvements to the Tactus model is our use of a recursive sampling technique that uses sparse localized attention rather than Tactus's global attention mechanism for doing its sampling. This significantly reduces the computational complexity because we're only considering the most relevant data for performing the sampling, as opposed to considering all the data. And it also enables you to significantly speed up that sampling because you can perform multiple samples within the same time series at the same time. Next slide, please. So, as an overview of the complexity improvements that we can achieve with our modifications, if n is the total number of variables that we have within our time series, d is the total number of different types of observations that we're considering, and t is roughly the number of time steps within the time series. Tactus originally has a quadratic requirement of memory, so it scales according to n squared in terms of memory, and we can reduce that to a linear dependence. So we're going down to an order of m times n, where m is a very small constant compared to the number of total number of variables that we're considering. And in terms of the time it takes to perform sampling, we go from order of n for Tactus down to a logarithmic time complexity, at least for sampling. So these are significant complexity improvements that this model or our improvements can offer. Next slide, please. So as an overview of our data processing pipeline. Modeling asynchronously observed time series data really is a challenging problem of missing data inference. And we're developing an improved architecture that can substantially reduce the computational burden of performing inference for asynchronously observed time series. And with these gains in computational efficiency, you can incorporate more information into your models, and you can still maintain the same budget for your computational resources. Thank you.
Thanks, Chris. We'll pivot over to Siri now, who will talk about a potential OR-driven framework to provide useful analysis given the data analysis that Chris just described could be applied to the PPMX data set. So Siri, I'll hand it over to you now.
So now I'm going to talk about the scheduling problem to help reduce maintenance cost. So now consider a setting in which there are M vehicles and M is very large. So each vehicle has its own condition. So this system's dynamics in this time horizon tau develop as follows. So at the beginning of each time period T, a decision maker actually will change the conditions of selective vehicles, which basically means for each vehicle, we need to make a decision which part we want to maintain. So to which condition we want to change the condition now. So it basically is called the maintenance stage. And in each period after this decision was made and the maintenance has been completed, the nature will changes the condition of all vehicles. This is called the damage stage, which basically means each vehicle will randomly degrade its condition, or maybe it can fail, maybe just degrade. So under the constraint of budget for maintenance, the decision maker needs to decide the maintenance schedule to minimize the cost induced by potential failures. Okay, next slide, please. So the mathematical formula for the maintenance cost is as follows. So X, Y, Z here are conditions of vehicles, and W, X, Y is the maintenance cost if we want to change the condition of this vehicle from X to Y. And A prime T X Y is the number of vehicles that we plan to maintain such that its condition will change from X to Y. And kappa XY is the damage cost from condition Y to Z, which basically means, which specifically refer to the case that the nature just failed this vehicle, and then it will cause some immediate cost. Okay, and then the rest of part is kind of simpler. Beta T prime Y is the number of vehicles after we complete the maintenance. After we complete the maintenance, the number of vehicles in condition Y. And ZIY is, if you look at the number I vehicle in condition Y, so the nature will degrade it randomly. So it is a random outcome of the number I vehicle in condition Y after the nature try to degrade it. Then we are trying to minimize the expectation of this random cost in total under the budget constraint, because the sum of all the maintenance cost cannot be larger than some threshold. So it is a constraint of budget. Next slide, please. Yes, so now we talk about some proposed solution and challenges here. So when M is very large, we propose to use the mean field method, which is a modern method, to provide an approximate optimal solution. So when M is very large, the system becomes very complicated, and the mean field method tend to simplify the problem and make it tractable. But one challenge here is like the condition space of the vehicle can be very large, because as Chris and Patrick mentioned before, the vehicles have many subsystems, and each subsystem have their own condition. So the condition space of this whole vehicle, these systems in a vehicle can be very large, high dimensional, and can be continuous. So now one solution to that can probably be we discretize this condition space. Then another challenge is on how to measure the damage cost, which means how to measure the cost if a vehicle degrade from condition Y to condition Z, but it hasn't failed now. So one choice is to use the probability of failure in some time interval to measure this damage cost, basically scalar by the immediate cost itself. Yes, so this is basically my part about the scheduling problem. Thank you.
Thank you, Suri. Just to summarize the remarks and applicability to this initiative, Chris's research improving tactics is likely useful to the PPMX initiative, given its applicability to high dimensional data sets, which he directly mentioned with missing values and this is asynchronous, which are attributes to vehicle maintenance data sets, to all of them. And Suri has produced a potential direct mathematical formulation for improving maintenance at large for a program, given accurate data, which is what kind of the first stage of our analysis looks to provide. Just some upcoming timeline remarks. This winter, we're completing a paper that is being worked in parallel with this, an academic effort using distributionally robust optimization, specifically applied to extreme value theory, which it will be more theoretical in theme, but will likely be applied to the PPMX data set as well. And then by no later than the spring of 23, using the analysis that we've talked through on this discussion, we will complete a white paper with a detailed formulation of the data processing discussed by Chris. So we'll apply his methodology, and then the OR optimization that was discussed by Suri, that works most well with the data and the outcomes looked for by the program manager for PPMX. We appreciate your time, and thank you.